let's just jump right into this explainer. Today, we are looking at a massive and frankly almost intimidating mathematical machine known as the Adelic Langlands Program. We're going to explore exactly how this beast acts as an immense stress test, essentially taking a famous combinatorial puzzle and translating it entirely into a spectral geometric framework. It is absolutely fascinating. Here's our quick roadmap for today's explainer. First, the conjecture and assumption. Second, the translation pipeline. Third, constructing Adelic indicators. Fourth, the analytic engine crashes. And fifth, the geometric prime collapse.
All right, starting with part 1, the conjecture and assumption.
So, the Herzog-Schönheim conjecture states that if a group is partitioned into a finite collection of disjoint left cosets, their indices simply cannot all be distinct. Remember, these indices basically dictate the size or the frequency of those cosets. At first glance, it's just a seemingly simple discrete combinatorial puzzle.
But here's where it gets really interesting. The source material introduces this rogue assumption to put the conjecture to the test. What if the indices strictly are distinct? Like, what if the maximum index is entirely unique? Basically, this is the bad data we are intentionally feeding into our mathematical stress test to see exactly how and why it completely breaks the machinery.
Moving right along to section 2, the translation pipeline. Okay, so this sets up a highly rigid, three-part pipeline that our rogue assumption somehow has to survive. First up, an algebraic lift mapping discrete data straight to continuous Adels. Phase 2 is an analytic trace evaluating spectral data. And finally, phase 3, a geometric collapse on the Hitchin fibration.
Looking at the big picture here, you can really see how we take a problem in one language and translate it straight down. We're literally moving from discrete coset partitions to smooth, continuous Adels, then into spectral L functions, and finally down to this destructive interference that forces an absolute physical impossibility. It's like a giant translation engine.
That brings us to section 3, constructing Adelic indicators.
Now, to actually pull this off, the framework relies heavily on local Haar measures and Hecke eigenvalues. It really helps to just think of these as translation tools. They map discrete combinatorial indices directly onto the continuous automorphic spectrum. Essentially, they're taking our finite partitions and lifting them up into smooth, locally constant functions.
Take a look at how this equation unfolds, reading it left to right. We are constructing an Adelic indicator function here through a tensor product over all primes. And what's super cool is that you can physically see the combinatorial index, that di from our original conjecture, literally become the inverse local Haar measure right down at the bottom. The math here is directly converting a simple integer index into an actual spatial volume.
And if we follow the integral, we start seeing convolution operators acting through the local Hecke algebra. What it's doing is averaging the function over local translation orbits and then projecting it to Hecke eigenvalues. So, we've successfully converted a combinatorial covering into a very strict spectral rigidity condition.
But, this raises a rather terrifying mathematical question. Remember that rogue assumption we threw in earlier? Well, what happens when distinct support structures, which are born directly from that assumption of strictly distinct indices, generate completely decoupled eigenvalues?
Well, this leads us right into our first major crash. Distinct indices force distinct local Haar measures, and when passed through the Hecke algebra, they map to completely decoupled systems of eigenvalues. This generates a massively overdetermined system of spectral constraints. Basically, the distinct conjugacy classes in the Langlands pool group just collide destructively, and it completely shatters the global analytic continuity.
Which brings us to section 4, the analytic engine crashes. So it actually turns out that the core strategy being used here is surprisingly identical to some older, much more familiar concepts. Think about finding roots of unity on a complex unit disk using generating functions. It's the exact same idea. We are really just swapping out the tools. Looking at this comparison, you can see how the modern machinery is doing the exact same job, just scaled way up. Where the classical method uses generating functions to force an isolated pole, the Adelic framework uses automorphic L functions. It uses them to search for uncompensated poles across the entire automorphic spectrum.
Let's take a closer look at how the Selberg Trace Formula actually sets this up. As you can see, it perfectly equates a geometric side to a spectral side. On the geometric side, it computes the volumes of quotients to extract our index data, Meanwhile, on the spectral side, it computes the trace of convolution operators on the space of automorphic forms.
Now, because our covering is exact, the sum of all our components absolutely must equal the constant baseline. The catch? The baseline L function has a rigid, completely unmovable simple pole at s equals 1, which really forces us to ask, can distinct, non-isomorphic cuspadal representations actually balance that global pole perfectly?
Well, by the Jacquet-Schillick rigidity theorems, the L functions of distinct cuspadal representations have residues that are strictly 0. So, looking directly at the equation here, 0 plus 0 plus 0 absolutely does not equal a pole at s equals 1. The left side is completely finite, but the right side is infinite. It's a literal structural singularity mismatch, a huge mathematical contradiction.
And that leads to our final phase, section 5, the geometric prime collapse.
Under this specific framework, our data gets mapped to sheaves on a prime fiber. But what exactly happens to a geometric, physical shape when its topological phases, which, remember, are driven by our distinct indices, lack the symmetric pairs needed to cancel out locally?
Well, because of those distinct indices we forced in, asymmetric Galois monodromy pushes the Fourier-Mukai transform entirely outside the support of the dual algebraic cycles. Notice right here how this destructive interference forces the intersection integral to just equal 0. But we know the sum has to match the baseline, right? And a smooth abelian Prym variety simply cannot have a volume of 0. It's impossible.
So, summarizing this incredible mathematical stress test, we've seen that forcing that rogue assumption through the pipeline guaranteed structural failure across 3 entirely different domains. We had a spectral conflict, a massive analytic crash, and finally a geometric collapse. Ultimately, the Herzog-Schönheim conjecture definitely holds up, because strictly distinct indices just simply cannot exist mathematically.
Which leaves us with this final thought. If this immense translation engine can completely dismantle this impossible assumption, literally linking combinatorial integers to continuous volumes, spectral traces, and complex geometry, what other profound mysteries could the Langlands program decode in the future? I really hope this explainer leaves you marveling at the sheer unifying power of this machinery and honestly, just hungry to learn more.